It's difficult for us humans to fully comprehend the enormity of space. We're comfortable in our own cosmic neighborhood, the solar system, and are used to familiar faces like Jupiter, Mars, and of course Earth. But beyond the heliopause lies the cold oblivion of interstellar space. Only 3 confirmed objects have ever crossed this threshold into our domain. These were the famous Oumuamua in 2017, Borisov in 2019, and now 3IATLAS in 2025, visitors that bring with them both scientific excitement and perhaps even a hint of cosmic fear about what else might be traveling between the stars. Beyond the heliopause, our interstellar visitors. The vast expanse beyond our solar system represents one of the most hostile environments imaginable. A realm where temperatures approach absolute zero, and the nearest stars are separated by trillions of miles of empty void. Yet occasionally, objects from these distant stellar nurseries complete journeys lasting millions of years to visit our cosmic neighborhood. Interstellar space begins beyond the heliopause, approximately 120 astronomical units from the Sun, where our star's solar wind can no longer push back against the interstellar medium. Dr. Alan Stern from the Southwest Research Institute describes this boundary as humanity's cosmic doorstep, beyond which lies the true wilderness of the galaxy. The detection of interstellar visitors requires objects to exhibit hyperbolic orbits, trajectories that prove they're not gravitationally bound to our Sun and must have originated elsewhere. NASA's definition requires orbital eccentricity greater than 1.0 and excess velocity that cannot be explained by gravitational acceleration from solar system bodies. These mathematical signatures distinguish true interstellar objects from long-period comets that merely appear to come from great distances. The rarity of such detections makes each visitor precious, windows into the composition and formation processes of distant planetary systems that we may never reach with conventional spacecraft. The third visitor, 3I/Atlas discovery. January 2, 2025 marked a historic day in astronomy when the Atlas Asteroid Survey detected an unusual object that would soon become our third confirmed interstellar visitor. Dr. Larry Deneau from the University of Hawaii was monitoring the automated detection systems when object A11PL3Z appeared in the survey data, moving at an extraordinary velocity that immediately flagged it as anomalous. Unlike typical asteroids that follow predictable elliptical orbits, this object displayed hyperbolic motion characteristic of visitors from interstellar space. Dr. Robert Warwick, the astronomer who discovered both Oumuamua and helped confirm Borisov, led the initial follow-up observations that confirmed the object's interstellar origin. The Minor Planet Center in Cambridge, Massachusetts coordinated rapid confirmation observations from telescopes worldwide, including the Canada-France-Hawaii Telescope and Gemini Observatory. Within 72 hours, enough orbital data had been collected to definitively prove that A11PL3Z was traveling too fast to be gravitationally bound to our solar system. The object's discovery represents a milestone in astronomical detection capabilities, the first interstellar visitor found by automated survey systems rather than manual observation. 3I/Atlas received its final designation after the International Astronomical Union confirmed its interstellar trajectory and cometary activity, making it officially the third known visitor from beyond our solar system. The ATLAS Survey System. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, represents a revolutionary approach to sky surveillance, designed primarily to detect potentially hazardous asteroids, but proving equally capable of finding interstellar visitors. Dr. John Tonry from the University of Hawaii leads the project, which operates 4 telescopes across Hawaii and South Africa, continuously scanning the entire visible sky every 24 hours. Each ATLAS telescope uses a 0.5-meter mirror equipped with advanced CCD cameras, capable of detecting objects as faint as magnitude 19.5. The system processes approximately 100 terabytes of data monthly, using sophisticated algorithms to identify moving objects against the background of stars. ATLAS distinguishes itself through rapid cadence observations, taking multiple images of the same sky regions within hours to detect object motion. The discovery of 3I/Atlas validated the system's ability to detect rare phenomena beyond its primary mission. Dr. Deneau noted that the automated nature of ATLAS allows us to catch objects that human observers might miss due to their subtle motion or unusual characteristics. The system's success has prompted NASA to fund expansion to additional sites, creating a global network capable of providing even earlier warnings for both hazardous asteroids and interstellar visitors that might otherwise escape detection. From A11PL3Z to C2025N1, the naming journey. The designation journey of 3I/Atlas really illustrates the complex process astronomers use to classify and name celestial objects. So, initially it was designated A11PL3Z by the ATLAS survey system, but, as its true nature became apparent, the object underwent multiple reclassifications. Dr. Gareth Williams at the Minor Planet Center explained that automated survey systems use temporary alphanumeric codes before official designations are assigned. Once hyperbolic orbital motion was confirmed, the object received the provisional designation C/2025N1, which indicates a comet discovered in the first half of July 2025. The C/prefix denotes a non-periodic comet, while 2025N1 tells us it was the first comet found during the 14th half-month period of that year. As observations revealed clear cometary activity, including coma formation and tail development, the International Astronomical Union assigned the final designation 3I/Atlas. The 3I prefix marks it as the third interstellar object, following 1I/Oumuamua and 2I/Borisov. The Atlas portion honors the survey system that discovered it, following IAU traditions of crediting discoverers. This naming evolution really reflects the careful verification process required to confirm interstellar origin, ensuring that only objects with definitively hyperbolic orbits receive the prestigious EIN designation reserved for visitors from other star systems. A hyperbolic journey at 58 kilometers per second. 3I/Atlas approaches our solar system with a hyperbolic excess velocity of 58 kilometers per second, a speed that definitively proves its interstellar origin and provides clues about its cosmic journey. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory calculated that this velocity places 3I/Atlas among the fastest interstellar visitors ever detected, suggesting either a recent gravitational encounter with another star, or acceleration from its parent system. The object's trajectory indicates it entered our solar system from the direction of the constellation Lynx, possibly originating from the Vega stellar system, which is about 25 light-years away. Orbital mechanics reveal that 3I/Atlas has been traveling through interstellar space for an estimated 1 to 3 million years before encountering our solar system's gravitational influence. The object's perihelion, its closest approach to the Sun, occurred on October 30, 2025, at a distance of 0.65 astronomical units, which is well within Earth's orbital radius. Dr. Alan Harris from the German Aerospace Center noted that this close solar approach provides optimal conditions for studying the object's composition through spectroscopic analysis and thermal emission observations. The hyperbolic nature of the orbit means 3I/Atlas will never return. After its solar encounter, the object will be gravitationally accelerated by our Sun, eventually reaching speeds exceeding 70 kilometers per second as it exits toward the constellation Draco. Brightness, rotation, and the 29-hour cycle. Photometric observations of 3I/Atlas have revealed a complex 29-hour rotation period that provides crucial insights into the object's shape, composition, and structural integrity. Dr. Alan Fitzsimmons from Queen's University Belfast leads the International Photometry Campaign, coordinating observations from telescopes worldwide to track the object's brightness variations over time. The 29-hour cycle shows magnitude variations of approximately 1.5, which indicates either a highly elongated shape similar to Oumuamua or surface features with dramatically different reflectivity properties. Light curve analysis by Dr. Mikael Granvik from the University of Helsinki suggests the object is likely tumbling rather than rotating around a single axis, which is consistent with an object that has experienced gravitational perturbations or impacts during its interstellar journey. The rotation period is significantly longer than typical solar system comets, which usually rotate every 6 to 12 hours due to outgassing torques. Thermal infrared observations using the Spitzer Space Telescope show that 3I/Atlas maintains surface temperatures consistent with its distance from the Sun, but with unusual temperature distribution patterns that suggest non-uniform surface composition. The object's brightness peaked at approximately magnitude 10 during perihelion, making it visible to experienced amateur astronomers using moderate-sized telescopes, but remaining too faint for naked-eye observation, despite its considerable size. Coma, tail, and cometary activity. Unlike the mysterious Oumuamua, 3IATLAS displays clear cometary activity which has, provided astronomers with valuable data about its composition and structure. Dr. Matthew Knight from the University of Maryland leads studies of the object's coma, the fuzzy atmosphere of gas and dust surrounding the nucleus as solar heating vaporizes surface materials. The coma began developing when 3IATLAS reached approximately 2.5 astronomical units from the Sun, initially appearing as a faint envelope around the central nucleus. Spectroscopic analysis by Dr. Michael DeSanti from NASA Goddard Space Flight Center detected emissions from water vapor, carbon monoxide, and hydrogen cyanide, typical signatures of comet sublimation, but with unusual abundance ratios. The object developed a visible tail reaching lengths of 200,000 kilometers as it approached perihelion, composed primarily of dust particles ejected by outgassing. High-resolution imaging from the Hubble Space Telescope revealed the tail's structure shows periodic variations corresponding to the object's rotation, indicating active regions on the nucleus surface. Dr. Jacqueline Keene from Boston University noted that the gas production rate of 3IATLAS is approximately 10 times higher than expected for its estimated size, suggesting either unusual composition or internal structure. The cometary activity confirms 3IATLAS as a volatile-rich object that formed in the outer regions of another stellar system, where temperatures were low enough for water and other compounds to condense. Oumuamua versus Borisov versus 3I/Atlas. So let's compare these three confirmed interstellar visitors: Oumuamua, Borisov, and 3I/Atlas. They really present a fascinating study in contrasts, revealing just how diverse the objects traveling between stellar systems can be. Oumuamua, which was discovered by Dr. Robert Warwick back in 2017, is still the most enigmatic of the bunch. It showed no cometary activity, even when it got close to the Sun, and it had this unexplained acceleration and extreme elongation that made it, well, truly unique among known solar system objects. On the other hand, 2I Borisov, which was found by amateur astronomer Gennady Borisov in 2019, behaved exactly as astronomers expected an interstellar comet would. It developed a classic tail, showed predictable outgassing, and had a composition pretty similar to solar system comets. Then there's 3IATLAS, which represents something kind of in-between. It displayed clear cometary activity but with some unusual characteristics that set it apart from typical comets. Dr. Stefano Bagnulo from Queen's University Belfast led comparative studies showing that Borisov had carbon monoxide ratios similar to solar system comets, while 3IATLAS showed significantly different volatile abundances. When it comes to size, estimates put Oumuamua at around 400 meters long, Borisov at roughly 1 kilometer in diameter, and 3IATLAS at an estimated 5 to 10 kilometers across, making it potentially the largest interstellar visitor we've detected so far. All this suggests that Oumuamua might represent a rare class of objects, while Borisov and 3IATLAS indicate that typical interstellar comets actually share a lot of characteristics with their solar system cousins. A 3 billion 11-year-old traveler. Determining the age of 3IATLAS is, honestly, one of the most challenging aspects of studying interstellar objects. It requires some pretty sophisticated modeling of cosmic weathering processes and orbital dynamics. Dr. Grigory Fedorets from Queen's University Belfast estimated the object's age to be somewhere between 3 and 11 billion years, based on its surface spectroscopic properties, and assumed travel times from nearby stellar systems. That's pretty wild. It means 3IATLAS could be older than Earth itself, having formed during those early epochs of galactic evolution, when star formation rates were way higher than they are today. Now, cosmic ray exposure modeling by Dr. Renu Malhotra from the University of Arizona suggests the surface should show significant radiation damage after billions of years in interstellar space, but interestingly, observations indicate a surprisingly pristine composition. The age estimates assume 3IATLAS originated from stellar systems within 100 light-years of our current galactic position, though honestly the actual birthplace could be much farther away. given the complex orbital motions of stars over galactic timescales. Dr. Fatih Namouni from Côte d'Azur Observatory calculated that objects of this age could have originated from star-forming regions that no longer even exist, having been dispersed by galactic rotation and stellar evolution. The ancient nature of 3IATLAS gives us, well, a unique opportunity to study materials from the early solar system formation epoch, potentially preserving chemical signatures from primordial stellar nebulae that formed billions of years ago. October 30th, perihelion and beyond. October 30th, 2025 marked the closest approach of 3IATLAS to our Sun, giving astronomers around the world optimal conditions for detailed study of this ancient interstellar visitor. Perihelion observations coordinated by Dr. Casey Lise from Johns Hopkins Applied Physics Laboratory used, honestly, just about every major ground-based observatory and space telescope to capture as much scientific data as possible. The 0.65 AU closest approach placed 3IATLAS well within Earth's orbit, allowing for unprecedented resolution observations of an interstellar object's nucleus and its active regions. Solar heating during perihelion triggered peak cometary activity with gas production rates reaching 10 to the 28th molecules per second and a tail stretching over 500,000 kilometers. Dr. Tony Farnham from the University of Maryland reported that high-resolution imaging revealed surface features and active jets similar to solar system comets, but, interestingly, with some unusual spatial distribution patterns. After perihelion, tracking shows that 3IATLAS will stay observable until about mid-2026 before fading beyond the detection limits of our current telescopes. The object's exit trajectory toward the Draco constellation has been calculated with precision, with a final velocity exceeding 75 kilometers per second as it leaves our solar system for good. Looking forward, future observations will focus on long-term monitoring of the tail's evolution and spectroscopic analysis of outgassing products, which will keep revealing secrets about interstellar comet formation and the chemical evolution of distant planetary systems. 3IATLAS has given astronomers an unprecedented opportunity to study pristine material from another star system, bridging billions of years and countless light years to reach, well, our cosmic doorstep. This ancient traveler carries chemical signatures from stellar environments we may never visit, and its cometary activity proves that familiar processes are at work throughout the galaxy. As 3IATLAS continues its eternal journey beyond our solar system, it leaves behind invaluable data that expands our understanding of planetary formation all across the cosmos. Be sure to subscribe to Stellar Tech for more discoveries about our universe's most distant messengers.